Our universe, for instance, is the Smoothway universe, and the closest world to us is the Andromeda universe. It is estimated that there are around 100 billion galaxies in the observable universe. The Andromeda Galaxy has been instrumental in reshaping our understanding of the cosmos and our place within it. While our universe is the Smoothway, the closest galaxy to us is Andromeda. This discovery provided undeniable evidence that the universe and the concept of creation do not revolve around Earth, shattering the belief that the Smoothway was the only galaxy in existence. It suggested that we are just a small part of an enormous cosmos. Our knowledge of Andromeda has expanded significantly over the past century, primarily through observations made on Earth. With advanced tools like the James Webb Space Telescope, JWST, now at our disposal, our perspective has dramatically shifted. Shockingly, recent data from the JWST has challenged our previous understanding of Andromeda, presenting new cosmic mysteries to unravel. The JWST has detected strange signals coming from our neighboring galaxy, leaving the scientific community astounded. Join us as we explore how the JWST picked up these disturbing signals from the Andromeda Galaxy. The concept of the Smoothway has evolved throughout human history, shaped by our growing comprehension of the universe. In ancient times, when our technological capabilities were limited, the Smoothway appeared as a faint band of light across the night sky, giving rise to various interpretations and legends. It was often considered a mystical and central feature in the cosmological beliefs of many cultures. In the 1920s, American astronomer Edwin Hubble made a groundbreaking discovery using the 100-inch Hooker telescope at Mount Wilson Observatory. Through observations and analysis, Hubble showed that distant clouds beyond the Smoothway were actually separate galaxies, each containing billions of stars. One of the closest of these galaxies was the Andromeda Galaxy, also known as M31. Andromeda has a rich history of observations dating back centuries. The earliest known record of this celestial object can be traced back to the 10th century, when the Persian astronomer Abdul Aleman al-Sufi described it as a small cloud in star charts from that time. The significance of these observations lies in the fact that al-Sufi was able to identify this distant celestial feature without the aid of telescopes, relying solely on his sharp vision and observations. In 1612, Simon Marius, based on telescopic observations, provided a more detailed description of the Andromeda Galaxy. His work laid the foundation for future astronomers to study this vast cosmic structure. In 1764, the famous French astronomer Charles Messier catalogued the Andromeda Galaxy as M31 in his renowned Messier catalogue, wrongly attributing its discovery to Simon Marius, who was aware of al-Sufi's earlier work. Nevertheless, Messier played a significant role in putting Andromeda on the map, and for nearly 100 years afterward, astronomers worldwide continued to investigate this mysterious galaxy, each contributing to the discoveries of the others. Before that, in the early 17th century, Italian astronomer Galileo Galilei revolutionized our understanding of the Smoothway. Using his newly developed telescope, he made key observations that challenged the prevailing Aristotelian cosmology. He discovered that the Smoothway was not just a diffuse band of light, but rather a vast collection of individual stars, planets, and other celestial objects. Through his observations, Galileo demonstrated that the Smoothway was not at the center of the universe, as had previously been believed, but rather a large region of stars scattered throughout space. In 1750, English astronomer Thomas Wright proposed a new theory in his work A New Hypothesis or A New Theory of the Universe. According to Wright's hypothesis, the Smoothway was not a random distribution of stars in space but rather a flat plane of stars. He also suggested that part of this vast structure was our own solar system. While Wright's theory was a step forward in understanding the structure of the Smoothway, it was still limited by the observational technology available at the time. Astronomers still believed that the Smoothway was the only galaxy in existence, given the technological constraints. A major leap in understanding the Andromeda Galaxy came in 1864 when English astronomer William Huggins made a significant observation. He studied the spectrum of Andromeda and noted that it was different from that of a typical nebula. This cleared the way for the world to finally recognize Andromeda for what it truly is: a galaxy in its own right. Andromeda has a mass estimated to be between 1 and 2 trillion times that of our Sun. It is a colossal cosmic structure that happens to be located relatively close to us in the vastness of space. All the research conducted up to now has led scientists to believe that Andromeda is about 10 billion years old, making it ancient by cosmic standards. Its age suggests a long and complex history of development and evolution. One intriguing aspect of Andromeda's origin is the theory that it formed through the merger of several smaller protogalaxies. This implies that over billions of years, smaller cosmic objects gradually came together under the force of gravity to form the magnificent Andromeda Galaxy we see today. Such cosmic mergers are common events in the universe, playing a key role in the formation and structure of galaxies. For many years, astronomers believed that Andromeda was significantly larger than our own Smooth-Way galaxy. From an observational perspective, this mistake was easy to make, as we are located within our own galaxy, and viewing Andromeda from Earth makes it appear so enormous that one might easily assume it is vastly bigger than the Smooth-Way. However, this is not the case. Galaxies are vast systems, and their mass is intricately linked to the distribution and movements of stars, gas, dust, and dark matter within them. Pinpointing these values with precision is a challenging task that requires advanced observational techniques and meticulous analysis. This kind of work would not have been possible in the 1700s or even the 1800s. It requires modern instruments, which is why this information has only come to light in recent years. Recent discoveries have led to a reassessment of these beliefs, with new findings prompting scientists to slightly revise their estimates of Andromeda's mass. As the mass of the universe continues to expand, our understanding of space has evolved significantly. One key revelation is how much closer the masses of the Milky Way and Andromeda galaxies are than previously thought. If you were located in Andromeda and looked toward Earth, you would perceive a universe that seems just as vast as our own. This offers a new perspective on the sheer size of the Milky Way itself. Andromeda's actual size, however, is something astronomers have thoroughly studied. It is known to span a remarkable 220,000 light-years in diameter, making it significantly larger than the Milky Way, whose estimated diameter is between 100,000 and 175,000 light-years. This update also highlights the complexities of accurately measuring the mass of galaxies. At the center of the Andromeda Galaxy lies an immense supermassive black hole, which exerts a powerful gravitational pull on the surrounding stars. These stars orbit the black hole in elliptical paths, similar to how planets orbit the Sun. At a certain point in their orbits, stars come closest to the black hole in what is known as the perihelion. Here the gravitational forces are at their peak, causing the stars to move at their highest speeds. This intense gravitational interaction causes the stars to crowd together, emitting energy in the form of radiation, including visible light and various types of electromagnetic radiation. This concentration of stars and radiation creates a bright central region, which is observed by astronomers as the active galactic nucleus, AGN, of Andromeda. An AGN is a highly energetic region found at the core of galaxies, fueled by the presence of a supermassive black hole. These black holes are incredibly dense, with enormous amounts of mass concentrated in a small space. When astronomers observe AGNs using advanced telescopes like Hubble, they often see a fascinating phenomenon. Andromeda's AGN appears to have two distinct focal points, indicating two regions of intense radiation emission. This second focal point lies just off the galaxy's center, where a massive black hole resides, with its mass estimated between 110 to 230 million times that of our Sun. Supermassive black holes are common in the centers of galaxies, including our own Milky Way, and they play a vital role in the evolution and dynamics of galaxies. When matter, such as gas and stars, gets too close to a supermassive black hole, it forms an accretion disk around it. This disk of swirling material heats up and radiates intense energy across various frequencies, which is why AGNs are so luminous. The Andromeda Galaxy is also home to an abundance of globular clusters, dense groups of stars that orbit the galaxy's core. These clusters, numbering around 460, contain hundreds of thousands to millions of stars each, and their presence sheds light on Andromeda's history. These clusters suggest that Andromeda has likely consumed many smaller galaxies over the course of billions of years, a process known as galactic cannibalism. As smaller galaxies fall within Andromeda's gravitational influence, they are torn apart, with their stars being absorbed into the larger galaxy's population, adding to its rich star diversity. This process of merging and gathering stars from smaller galaxies is typical of spiral galaxies like Andromeda. In addition to its striking features, recent observations have led astronomers to propose that Andromeda may be undergoing an intriguing transformation. It seems to be transitioning from a classic spiral galaxy to a rarer type known as a ring galaxy. These galaxies are characterized by a circular or ring-like structure made up of young, bright, blue stars, while the central region contains relatively little radiant matter. This distinctive feature sets ring galaxies apart from other galactic structures. There are three primary types of ring galaxies: optical rings, atomic rings, and inner and outer rings. Atomic rings are found near the center of a galaxy, while the inner and outer rings are located further out. Ring galaxies are further classified into two categories: O-type and P-type. O-type ring galaxies have smooth, regular rings with a central core, while P-type ring galaxies exhibit more irregular rings and a displaced central core. Astronomers believe that ring galaxies can form through two main processes: the collision of multiple galaxies or a smaller galaxy passing through the center of a larger one, triggering the formation of a ring structure. Notable examples of ring galaxies believed to have formed from cosmic collisions include the Cartwheel Galaxy. The Milky Way and Andromeda are on a collision course and will eventually merge to form a new supergalaxy. This event, while still far off, has already been dubbed with names like Mila, and while these names are playful, the consequences of such a merger for humanity could be catastrophic.